When an Arctic air mass hits the subtropical humidity of the Gulf Coast, moisture in the air crystallizes directly onto exposed industrial infrastructure. Within hours, mechanical systems designed to dissipate heat are locked in ice. During Winter Storm Uri in February 2021, this sudden temperature drop triggered a cascading failure. The resulting statewide blackout left 4.5 million Texans without power and caused the collapse of 38 public water systems. The property damage reached $18 billion in insured losses statewide, driven almost entirely by catastrophic pipe bursts. This presents a geographic paradox. Northern infrastructure functions in sub-zero conditions for months, yet Gulf Coast utilities fail after just 48 hours at 20 degrees Fahrenheit. Historically, Southern property management relied on a drip-and-pray methodology, leaving faucets dripping and depending on active interior building heat to keep wall cavities warm. But when the regional power grid fails, that active heating disappears. Securing these facilities requires abandoning historical assumptions and executing rigorous, data-driven technical audits of both passive and active thermal envelopes. True facility resilience is measured by the system's ability to survive the new, volatile climatic data baseline. Soil acts as the foundational thermal buffer for all subterranean water lines and industrial pipelines. In deep freeze environments like Chicago, municipalities mandate utility burial below the established frost line, typically 60 inches deep, safely insulating infrastructure from the freezing surface air. Along the Gulf Coast, historically mild winters and high water tables have normalized shallow utility trenches of merely 12 to 18 inches. Consider latent heat. When soil freezes, its temperature flattens at 32 degrees, releasing stored energy as an insulating blanket. A 60-inch trench provides massive thermal mass, protecting pipes for weeks. A shallow 12-inch trench has drastically less mass, exhausting its buffer in mere hours. Once that buffer is depleted, the ambient temperature around the pipe plummets, initiating internal freezing. Because Gulf Coast infrastructure cannot rely on geothermal soil buffering, the burden of freeze survival is shifted entirely onto the pipe's immediate physical materials. Water failure occurs because water undergoes a violent volumetric expansion when frozen. The molecules lock into a rigid crystalline lattice structure. During this phase change, freezing water expands its volume by roughly 9%. This expansion creates a hydraulic ram effect inside the plumbing. The force generates internal pressures exceeding 2,000 psi against the pipe walls. Rigid materials like copper, galvanized steel, and CPVC lack the flexibility to absorb this kinetic stress, resulting in catastrophic shear failure right through exterior brick. The primary defense against this hydraulic rupture is the installation of a passive thermal insulation envelope. However, high ambient moisture in the south creates a vulnerability known as the humidity insulation nexus. This is the dew point phenomenon. Warm, humid air hits a freeing pipe, transforming into liquid droplets underneath the insulation. The sealed vapor barrier is engineered to keep atmospheric moisture out. Any physical breach allows this moisture to infiltrate the thermal matrix. Once the insulation becomes wet, its thermal resistance value drops to zero. In a subtropical climate, this wet insulation becomes a vector for hazardous mold and microbial growth. When active heating is eliminated during a grid failure, a bone-dry passive thermal envelope is the only barrier against a 2,000 psi hydraulic rupture. For critical commercial and industrial piping, passive insulation is supplemented with electric heat tracing. These systems utilize self-regulating electrical cables that automatically adjust their wattage output based on the localized temperature of the pipe. Yet these systems suffer high failure rates due to installation errors and lack of diagnostic testing. A technical audit begins by verifying cable positioning. The Keating cable must be locked into the 5 o'clock or 7 o'clock position. This orientation optimizes upward heat transfer while preventing the cable from sitting in moisture pooling at the 6 o'clock baseline. Auditors must also verify service loops, an extra 1 to 2 feet of cable wrapped around high-mass heat sinks like valves, flanges, and pumps. Before applying outer insulation, electrical integrity must be confirmed using a megometer or Megger test. This test applies 1,000 volts of direct current through the circuit. It ensures the dielectric resistance is intact and the polymer insulation hasn't been damaged, which would create a ground fault risk. A healthy target reading is 2,000 megohms. Any reading below 20 megohms requires total replacement. Proper breaker sizing is equally critical. These systems must be wired to 30 mA ground fault equipment protection breakers, rather than standard 5 mA GFCIs. Because of their internal chemistry, self-regulating cables draw massive inrush currents upon a cold startup. That amperage spike will instantly cause a standard 5 mA breaker to execute a nuisance trip. An unaudited, incorrectly wired heat trace circuit offers no protection. If it grounds out or trips its breaker when freezing hits, the asset will be destroyed. These pipe vulnerabilities trigger the cascading failures uncovered by federal investigations following Winter Storm Uri. A report by the Federal Energy Regulatory Commission proved that infrastructural freezing caused over 75% of the region's unplanned power plant outages. The problem includes internal frost within midstream infrastructure. As natural gas expands at compressor stations, it drops below freezing due to the Joule-Thomson effect, causing frost jacking that damages supply lines. Responding to this grid instability, Gulf Coast municipalities aggressively adopted 2021 International Plumbing Code amendments. Under IPC Section 305.4, regulators no longer accept active heat as standalone protection for unconditioned spaces, because the regional power grid itself is not guaranteed. The new standard of care mandates that a facility's passive thermal defenses must be robust enough to survive a total blackout. Thermodynamic physics and code regulations have been consolidated into a definitive three-part audit protocol for Gulf Coast facility managers. Pillar 1. Physically inspect all passive vapor barriers. Ensure outer insulation jackets are perfectly sealed to prevent the dew point phenomenon from destroying the insulation. Pillar 2. Validate pressure relief paths. Ensure plumbing networks have functional relief valves to vent the 2,000 psi forces of ice expansion. Pillar 3. Mandate 1,000-volt dielectric Megger testing and verify proper 30 mA breaker sizing for all active heat trace circuits. Relying on historical weather patterns is a proven financial liability. Modern property management requires diagnostic engineering, not guesswork. True infrastructural resilience replaces historical assumptions with verified engineering standards. Be assured, be secured.